So our next speaker is Luciena Xiao, and they are a postdoctoral researcher in mathematics and statistics here in Helsinki. And they work on arithmetic geometry and representation theory. And they've just moved to us here in Helsinki in the past year, and previously they were in Paris and they got their PhD at Caltech. So we're really happy to have them with us here in Helsinki and also participating in today's event. So Luciena, please take it away.
Yeah, thank you, David, for the introduction. And it's my great pleasure to speak at this event. So broadly speaking, my research interests fall under the umbrella term of algebraic number theory. And it would be quite challenging for me to explain within 10 minutes what my research interests are. So let me just start by trying to explain to you what algebraic number theorists do. So algebraic number theorists are primarily interested in solution sets to polynomial equations. Well, what does that mean? Now, here is an example of a polynomial equation you've probably seen when you were in elementary school or middle school. That is a squared plus b squared is equal to c squared. So in this polynomial equation, we have three variables, a, b, and c, which represent numbers. So geometrically speaking, these three quantities correspond to the lengths of three sides of a right triangle, where the number c corresponds to the hypotenuse, which is the longest side. Okay. And we can be interested in solutions in, say, a certain category of numbers. Say we could be interested in solutions in real numbers or rational numbers or integers. Right, so from elementary school, you've probably seen the following triples that are solutions to this polynomial equation, namely the integers 3, 4, and 5 give you a set of integers such that, well, 3 squared plus 4 squared is equal to 25, which is 5 squared, right? Or you could also have 5, 12, 13, which gives you another triple that consists of integer solutions to this polynomial equation. Now, in fact, these Pythagorean triples were already known to Pythagoras, who lived, I think, in 600 BC. So this is the study of polynomial equations really date back to the very beginning of the history of mathematics. And in fact, this particular equation that we're looking at now have infinitely many solutions in the integers. And I'm going to tell you how do we find all of those solutions. Right, so since we want to find solutions in integers, we can perform the following change of variables. So let's let x to be a over c, and then let y to be b over c. Right, so since a, b, c are all integers, now a over c and b over c are going to be rational numbers. By definition, rational numbers are just quotients of integers. And since c stands for the length of the hypotenuse, which is the longest side of your triangle, we know that these quotients a over c and b over c are both less than 1. Okay. And after we perform this change of variable, namely we substitute x and y into this equation that we started with, we have x squared plus y squared is equal to 1. Now, geometrically, this equation now represents a circle in a plane that is centered at the origin and has radius 1. Okay, so now if I want to find a pair of numbers x and y that satisfy this solution, I just need to find a pair of rational points on this circle. Okay, so one way we can go about this is, well, if we connect the line that is determined by a point on the circle xy with this point on the left-hand side of the circle, which has coordinate -1, 0, then this is going to determine a unique line, which now intersects the vertical axis at one unique point, which has coordinates 0, t, where t is some number that lies between 0 and 1, because my circle has radius 1. Moreover, we can observe that this t is in fact also a rational number. Because using basic trigonometry, we have the following relationship between the quantity t, x, and y. Namely, if I look at this smaller triangle, which involves the point 0, t and the origin, then we know the ratio of this vertical side with the horizontal side is going to be equal to y over x, it's going to be equal to y over 1 plus x. So this gives us the relationship that t is equal to y over 1 plus x. Now, if we substitute this back into the equation x squared plus y squared is equal to 1, we can solve for x and y respectively in terms of t and obtain the following two expressions. Okay, so I have x is equal to this quotient and y is equal to this quotient involving t. Okay. And since we know t is a rational number, we can then express t as the ratio of two integers, p and q. And then we can substitute this back into the expressions of x and y in terms of t to get expressions of x and y now in terms of integers p and q. And then again, we can substitute these expressions back into our original equation, a squared plus b squared is equal to c squared, to obtain expressions of a, b, and c. So now since q and p are integers, these expressions in terms of q and p are also integers. So this will give us an integer solution to our original polynomial equation. For example, if you take the case t is equal to 1 over 2, so then p is equal to 1, q is equal to 2, and we recover the triple 3, 4, and 5, and so on. Now, since in the picture, I mentioned that this t is a rational number lying between 0 and 1, and there are infinitely many such rational numbers within this interval. So we also get an infinite number of solutions to this equation. And also there is a one-to-one correspondence between rational number t lying in this interval and pairs xy, which are solutions to this equation x squared plus y squared is equal to 1. So this expression that we obtain here in terms of q and p indeed give us all the solutions to this equation that we started with. Now in number theory, sometimes we're not only interested in the algebraic solutions to an equation, but we could also be interested in the entire solution set as a geometric object. Right? For example, if we think of this geometrically, then we have seen that this is just a circle. And we can in turn consider, well, what happens if I modify this equation a bit? So namely, what if we consider other circles? Right, then every circle centered at the origin is uniquely determined by its radius. Right, you give me a number that is a non-negative real number, and then I can draw a circle around the origin with that radius. And if you give me a circle around the origin, I can find its radius, which is now a non-negative real number. So this tells me that now if I consider this ray, which consists of the point 0 and the right and the positive half of the real line, then every point on this ray is going to correspond to one circle that's centered at the origin. And this kind of phenomenon is what we call a moduli space in mathematics. So a moduli space is just a space where every point of it corresponds to another kind of geometric object. And those geometric objects are always inherently related. For example, in the case of this ray, we want to look at all circles. And we want to tabulate how we can change between circles by moving inside this moduli space. So if I just take the point 1 in the moduli space and multiply it by 2, then well, the result I get geometrically is, well, I expand the circle's radius by 2. Right, so we get this kind of correspondence between how you can vary between points inside a moduli space versus how you can modify or how you can perturb your geometric object. Now, one kind of moduli space that I'm interested in is called Shimura varieties. So these are moduli spaces where each point corresponds to another geometric object called an abelian variety. Now, there are many different interpretations of abelian varieties. We could look at, we could think of them abstractly as solution sets to systems of polynomial equations, but then we could also think of complex solutions to those equations. Then inside the complex space, this just looks like a complex torus of some dimension n plus some additional properties. Okay, to visualize a torus, let's think of the following example of a real torus of dimension 2. Now, this can be obtained by taking a square and you identify its opposite edges pairwise. So this gives you a torus of dimension 2. To obtain a torus of dimension n, you just take, say, an n-dimensional analog of a square, identify its opposite size. Okay, so that's how you obtain an abelian variety geometrically. Now, a priori, if you find some parameter, which is like a point, which corresponds to an abelian variety, and you take the union of all of those points, you just get a set. You might not have something that has a nice geometric structure, which we had in the case of the moduli space of circles. Right, so now we might want to impose some additional properties so that we actually cut out a subset that has some nice geometric properties and whose symmetries we can study nicely. So this brings us to the notion of Schumann varieties. So this classify abelian varieties plus some additional structures. Okay. And one thing I studied in my PhD thesis is something called the Hecarim conjecture. So heuristically, it says that certain kinds of Schumann varieties, if you look at them from the modulo P perspective, they are going to look like Indra's net. So Indra's net is something that comes from a Hindu mantra. It's a net where at each intersection you get a water drop that reflects the entirety of the rest of the net inside itself. So on a modulo P reduction of a Schumann variety, you can move in two ways. And these two directions are horizontal to each other, which gives it a structure of a net. And then the Hecarim conjecture just tells you that these horizontal and vertical loci are precisely obtained by moving your abelian varieties in one way versus another. Okay, so that's a very vague explanation of what I did in my PhD thesis. So let me just talk very quickly about my experience as an LGBTQ person in STEM, because I think I'm running out of time, so I'll be brief. So I grew up in China. I was born and raised in China. And then I did a year of exchange in Bavaria in Germany during my high school. And I went to the United States for undergraduate and also graduate studies. And then I obtained my PhD last year and then moved to Paris for a year as a postdoctoral researcher. And then finally I moved here this year, again, as a postdoctoral researcher. So my experience in the academia has been roughly divided in 3 countries, the United States, France, and here. Overall speaking, I feel like my gender and sexual orientation does not really come into play inside the academia because in the mathematics milieu that I've been in, these are considered part of one's private life, and then people do not really ask you about these when you are just co-workers. But of course, these experiences might just be very specific to my own personal situations. But there has been a few situations where I find my gender identity very, very confusing. So I'm non-binary and gender fluid. And in mathematics and also in STEM more generally, there have been these initiatives to foster women mathematicians, like researchers or students. So there are these conferences or workshops that are for women or anyone who is women identified. And when I see advertisements for this kind of events, I never know if I'm qualified, because I do not necessarily always identify as a woman. So sometimes it feels like discrimination going the other way around because they're excluding everyone who is not a woman, namely they're excluding a man. And when I happen to identify as a man, I'm not eligible for these events. And on the other hand, it also feels like my gender identity is going against myself because as someone who's biologically female, I should be eligible for these events, but then now suddenly because my gender just varies towards the other end of the spectrum, I'm suddenly not qualified. Yeah, but luckily, I think these kind of situations or these confusions generally arise out of people's like non-deliberate ignorance of non-binary people. So whenever I see such an advertisement, I would maybe just email the organizer and then ask, well, are non-binary people welcomed? And usually they would respond and say yes. So I think it's just that they do not have the awareness of other gender and sexual minorities in the academia. So I think it's very important to raise that awareness. Okay, so I think I'll stop here and then maybe leave everything else for the panel discussion. Yeah, thank you for your attention.